Welcome to solverfy.
Okay, so for this problem, you have two loops that are separated by a lot, and this one has a bigger radius, r, and then this one has a littler radius, little r. This is constantly moving away, and the questions are basically like, well, what kind of EMF are you going to introduce into the loop? 1 second, let me check something. Yeah, so we first want to get the flux through the smaller loop and then the induced EMF and then the direction of the induced current. You could also ask what the induced current is for the other one. Could be an interesting problem, but luckily they asked this one. It's a little easier. So yeah, let's start this. So basically we want to get the flux first. Flux is going to be, in general, right, it's BA cosine theta, but there's B and A are always aligned if you make the area vectors. I guess it would be the area vector of this one that's relevant. So B and A are always parallel. So this bottom loop is creating, with its counterclockwise current, is sort of creating a field, which I'll draw in B, that's sort of coming up and making these types of loops. But by the right-hand rule, in the center, it's always up. And so to get the flux, what we need to do is we need to evaluate B and A. And so B is given by, you want to use the equation that they refer you to. So it's mu naught, the magnetic field due to this bottom loop for positions far away is mu naught times the magnetic dipole moment of the bottom, which is IA. And this area is this pi r squared. So it's the area of the bottom loop, because we're concerned with the field that one's making. This problem gets slightly confusing because there's two areas. So I wanted to make sure to outline that. And then just for copying the formula, it's 2 pi divided by x cubed. So the further you get, the smaller the flux. And then the area of the, and then we want the area intercepted. So that's going to be this area, this pi r squared. Hopefully this isn't too confusing. I'll call this a small, ASM for small, just to be totally clear and not reuse variables. And if you take this equation and simplify it, you might get what I got, which was mu naught I pi squared r squared. What a fun not pi squared, sorry. The pi's end up canceling, and it's pi big R squared times little r squared. And that's divided by 2x cubed. So that's the answer for A. And then for B, we want the EMF. The EMF is minus the time derivative of the flux. I guess this is actually a total derivative. I'm just going to quickly look that up to make sure that I'm writing this right. Small detail, but I don't think it's oh yeah, it is like a full derivative. So those should be D's, but whatever. Not a big deal. So d by dt of BA of this flux. So it's going to be minus d by dt of this. The only thing that depends on time is x implicitly. So I'm going to just take everything else and put it on the outside and write this. So, oops, almost forgot this little r squared divided by 2, and then d. Oh, what a d. Let me kill that. Dx No, not dx dt, sorry. D by dt of 1 over x cubed.
Yeah, so you're just setting it at the same parent. So we want to give it the same ancestry.
And so kind of by the chain rule, you can take the derivative of this with respect to x and then multiply by dx dt, which is the velocity. Taking the derivative of 1 over x cubed is minus 3 times x to the minus 4th. And so that's what you want to do to get your final answer. So mu naught I pi r squared divided by 2. And then this is x to the 4th. And we need a velocity. And then also times 3. And I'm just going to double check that that's all is needed. No, the direction of the induced current. So as this top loop is getting lifted away, its flux is decreasing. And so it's going to drive a current to keep it, to attempt to keep it at its original value. So it's going to be counterclockwise then, viewed from above, because a counterclockwise current in the top loop or in either loop will create a magnetic field that points up. So C counterclockwise. And let me just check one thing. Yes. Okay. Great.